Lean Six Sigma. My name is Frederico Aranha, but please call me Fred. I am a Lean Six Sigma Black Belt, and this is our last course in the Lean Six Sigma Green Belt learning path. In the present course, you'll learn advanced topics related to statistics and how to apply them into Lean Six Sigma. Before moving on, please be advised that I relied on Minitab to create portions of our course, Minitab being a statistical analysis software. Since Pluralsight has no courses on its library about Minitab, I chose not to create tutorials based on it, but rather demonstrate the results of calculations made on it so our students could watch this course even without knowing how to use this specific tool. Our present learning journey started with a course overview module, where I detailed all other modules in our training. However, let's quickly review our course's structure once more before I present you what is in for you by taking this module. So in this course, we will start by studying how to apply data to real-world situations, which is fundamental for those aspiring to lead Lean Six Sigma initiatives, since improvement projects will focus on actual problems. However, this is not going to be a hands-on module, but rather a presentation on the most widely adopted types of statistical distribution. We'll also study how to apply hypothesis testing, a central technique in Lean Six Sigma that is based on statistics and helps teams defining what is a problem and what is not, as well as validating improvements and alternatives. In presenting statistics in Lean Six Sigma, I will share with you best practices related to presentations and how to share information related to improvement projects with business executives and overall stakeholders, as well as best practices related to project management. At last, I'll share with you the Lean Six Sigma Green Belt certification exam syllabus and offer you sample exam questions so you can prepare yourself to take the test. This course is 100% based on the Lean Six Sigma Green Belt Certification Training Manual, which content was used with permission from the Council for Six Sigma Certification. You can download the training manual for free at sixsigmacouncil.org. This is an audio and visual representation of the official Green Belt publication produced based on Pluralsight instructional design guidelines and templates. Now, as for our present module, applying data to real-world situations, we'll study the following topics. Normal probability distributions, and in this specific video, I'll also talk more about what is in for you in this course and review essential statistic concepts. I'll also teach you how to use exponential distribution, log-normal distribution, the Weibull distribution, Cauchy, logistic and Laplace distribution, uniform beta, gamma, and triangular distributions, but that's not all. We'll also study binomial distribution and the binomial formula. I'll introduce you to the Poisson distribution and its equation, as well as how to calculate the Poisson distribution, and at last, I'll teach you about geometric distribution and negative binomial distribution. Back to Minitab. It offers a free trial of 30 days. You can download it at minitab.com. I'll offer you insights on how to use the tool as much as possible, but to keep our course accessible to a larger audience. As I already explained, I'll not focus on Minitab tutorials as we did with Microsoft Excel in our previous course in this learning path, Basic Lean Six Sigma Statistics. At last, before we dive in, please do not proceed if you did not watch our previous courses in the Green Belt learning path. They are mandatory for students willing to truly understand the content in this course. In this video, we're going to recall normal probability distributions, and I'll talk more about what is in for you in this module and in this course. While it's true that normal probability curve is the most important and commonly used distribution in statistics and by Six Sigma teams, it's also true that every set of data is not going to fall along the normal probability distribution. This module covers non-normal probability distributions, how to recognize some of the more common distributions through graphical analysis, and some information about using statistical analysis with such distributions. Some of the simpler statistical calculations for non-normal probability distributions are included in this module, along with details for how to handle those calculations manually. Calculations for all of the distributions mentioned are not included because they can be very complex and almost no one handles these calculations manually. Before moving forward, it's important to revisit some of the fundamental information about the normal curve. First, remember that the normal distribution is related to continuous data. This means that your data is associated with random variables that can take the form of any of an infinite number of points along an interval. Temperature over time is a continuous type of data. Yes, you might never see the temperature of a room fall below 40 degrees Fahrenheit, but within a range such as 40 degrees and 80 degrees, or an infinite number of continuous data points, if you measured to a high enough degree of accuracy. Remember that discrete data is not continuous in nature. Discrete data is typically about categorical occurrences. In some cases, discrete data can be converted to continuous data to allow Six Sigma teams to use more statistical analysis tools when working with the information. When that isn't possible, however, you cannot use the normal curve or related statistical analysis on discrete data. Discrete data usually involves either a binomial distribution or a Poisson distribution. Both will be covered later in this module. The normal curve, when presented in graphical format or on a histogram, is typically symmetrical in nature. The data elements tend to concentrate along the center of the curve, with elements fanning out slowly on either side as the curve drops ever towards zero. While a visual inspection of data through graphical analysis can help determine if data might be normal, there are several continuous distribution curves that look a lot like normal curves. That's why we apply statistical tests such as the chi-squared goodness of fit test to determine whether data is actually normal. Don't confuse the chi-squared goodness of fit test with the chi-squared distribution, which makes an appearance later in this module. One is a statistical test and the other is a probability distribution. The normal curve is symmetrical and is most commonly required for inferential statistics. It is described statistically using both the mean and standard deviation. The curve usually centers on the mean, and the number of standard deviations away from the mean changes the probability of the amount of data under the curve. That's it for a quick review and introduction of this module. I'll see you in our next video. In this video, we're going to study how to use exponential distribution. The exponential distribution creates a histogram or trend line that is exponential in nature. It decreases exponentially as you travel across the x-axis. See the image on your screen for an example. And on our example, you can see a chart based on temperature over time. In an exponential distribution, the data is not organized around the mean as in the normal probability curve, but at one end of the x-axis. The data used to create a histogram we just saw had a mean of 24.79, but a median of 16. Often, when working with non-normal data, the median is a more applicable data point than the mean for graphical analysis. If you locate a median on the x-axis of an exponential histogram, you know that 50% of the other data points fall before it and 50% after it. Exponential distributions are often used when working with datasets of time that include arrival times, the average or mean time between failures in the process, weight line theories, or the distance in time or space between interesting points of occurrence in data, processes, or experiments. Exponential distribution is particularly valuable when working with certain Poisson distributions. If you recall, Poisson distributions are discrete rather than continuous, which means Six Sigma teams are limited in what statistical tools can be used to analyze the data. However, the exponential distribution can often be used to describe the rate of change within the data that is distributed in a Poisson distribution, providing a method for creating continuous data that can be analyzed. The exponential curve never appears symmetrical. It is described statistically by the mean of the data in a value known as lambda. And here we have another graphical representation of an exponential distribution, which was generated in Minitab, which, as you already know, is a software that performs statistical analysis. Don't worry, you don't have to open Minitab now. As with the normal distribution, you can run a statistical test in Excel to determine if your data is exponential. The test is basically the same chi-squared goodness of fit test we studied in the previous course of the present learning path. The same idea is used. You first predict the number of data points you would find in each bin in a perfect exponential curve given the statistical data recording your set. You then compare the actual breakdown of your data against expected numbers to find the chi-squared value, which is used to evaluate your hypothesis that the data is exponential. Because we are going to introduce using Minitab for statistical analysis functions in the next modules, and because Minitab handles chi-squared goodness of fit testing and many other statistical calculations automatically, we won't cover detailed steps for testing each type of data distribution in Excel. Because most of the tests that can be performed using the free analysis toolpack in Excel require normally distributed data, the steps for testing for normal data in Excel should be sufficient for much of your Excel-only based work. Our last course was all about Excel, do you remember? In this video, we're going to study how to use log-normal distribution. At first, the log-normal distribution might appear to be an exponential distribution, but on graphical analysis, it is obviously constrained by zero. Pause the video and analyze the example chart you have on your screen. The log-normal distribution on a histogram is asymmetrical, with the trend line appearing more as a wave that moves across the page. The location and size of the wave varies with each dataset, and the shape can even be very different from the one you are seeing right now. Log-normal distributions are often used when working with datasets of time that describe time durations, such as the time a process or machine is down, or a distribution of assets or wealth among the population. Anytime data has a positive skew, which means the tail of the data is to the right, then a log-normal distribution might be possible. Consider the example of wealth within a population. If we only consider the amount of income each household within a population reports, almost no household will report an income of zero. And it's impossible to have an income of less than zero. Yes, you can have a net worth that is negative, and you can have a cash flow that is negative if you consider income and expenses. But for example, we're only discussing income. Now, in a random sample of income from across a large population, a city for example, data is likely to be log-normal. As you move further right in the bins on a histogram, representing increasing dollar figures of income, there are fewer households that will fall into each bin. As you reach the highest dollar bins, you'll likely see the fewest households represented on a histogram. While the effect is similar to the positive exponential distribution we saw in the sample chart I provided you in this video, there are some differences. The log-normal distribution of the wealth doesn't typically begin with the highest number of data points in the first bin. More often, you'll see a small number of or no data points in the first bin, followed by a quick rise to a median point and then a sloping trail to the right. The log-normal distribution typically describes a dataset with values in large ranges, can be described with both mean and standard deviation, and always has a positive skew. In this video, I'm going to quickly introduce you to the Weibull distribution. Just to make things more confusing, probabilities can fall into families of distributions, such as the Weibull distribution. Data that fits a distribution like the Weibull might also fit another distribution, including all of those discussed previously in this module. Note that the Weibull distributions relate to continuous data, so the data would not likely fit a discrete data distribution. Please pause the video now and look at the Weibull distributions I'm showing you on your screen, which were created using Minitab. Do these images look familiar? The curves appear to fit the log-normal, exponential, and normal distributions respectively, even though they each also fit the Weibull distribution. Weibull distributions can describe many data types and are often used when working with reliability applications and failure probabilities that change or vary with time. In this video, we'll cover Cauchy, logistic, and Laplace distributions. As previously stated, you commonly work with normal distributions when applying statistical analysis. Even if the underlying distribution of your dataset is not normal, if you have a large, random sample of continuous data, you're usually able to perform statistical analysis that are reserved for normal data, thanks to the central limit theorem. The central limit theorem states that the distribution of the mean of a large, identically distributed number of independent variables will approximate a normal curve. Because of this, you'll be able to use softwares like Minitab to apply statistical analysis to a number of datasets. It's still a good idea to be able to recognize common continuous distributions that are not normal. In this section, we'll highlight a few other non-normal continuous distributions and provide you with some sample images. In a graphical representation, the Cauchy distribution often looks like an elongated normal curve with a tire peak. While the Cauchy distribution does not share some characteristics with a normal curve, the data itself is not normal. In fact, the distribution doesn't have a defined mean or variance, which makes it not useful for many common statistical analysis tools used in Lean Six Sigma. The logistic distribution also appears to approximate the normal curve, and is in fact used in some science and math functions to approximate other symmetrical distributions. This is because the CDF of a logic distribution is more consistently calculable. Remember that the CDF is the cumulative density function and calculates the probability that a given data point is less than or equal to x, where x is any point on the x-axis of a probability curve. The Laplace distribution is often referred to as the bilateral exponential distribution or the double exponential distribution. You can see from the image on the screen, the Laplace distribution does seem to pair exponential distributions back to back. In this video, we're going to study uniform, beta, gamma, and triangular distributions. A uniform distribution occurs when data points are divided evenly among bins. Exact uniform distributions are almost never going to occur in randomly sampled data, which means Lean Six Sigma teams that see such distributions in data should check the authenticity of the data. Uniformity often points to an error of measurement, problem with the measurement system, a non-random sample, or an issue with the process. In some very specific cases, uniform distributions could point to success. For example, in a manufacturing plant, one machine might make dowels that are used later in the manufacturing process. If the dowels must measure 4 inches for functionality later, and a random sampling of dowels across all time buckets for the machine show 4-inch dowels being made, then uniformity equals success. Like Weibull distributions, beta distributions can take on a number of shapes, 2 of which are pictured on your screen. Beta distributions are considered extremely flexible and can become stand-ins for other distributions given certain statistical parameters. Gamma distributions are similar to beta and Weibull distributions, in that they take on a number of shapes. In fact, some distributions that aren't covered in this module are actually just more specific forms of the gamma distribution. Gamma distributions are, however, always skewed to the right. A triangular distribution is formed using the mode and upper and lower limits of a dataset. Pause the video and take a look on our sample. In this video, we will study binomial distribution. A binomial distribution is used when you are dealing with discrete data and there are only 2 outcomes for each trial or sample. In short, binomial distributions relate to attribute data. Yes or no, pass or fail, one or the other. A binomial distribution assumes that the outcome of any given trial is independent of the outcome of another trial. If you flip a coin, it will either be heads or tails. If you flip it again will be heads or tails, with a 50% probability for either outcome. It doesn't matter what happened with the first flip of the coin. In most cases, when considering attribute outcomes, the probability is not distributed evenly between the 2 events, as it is with a coin flip. Instead, there is a probability of success, notated as P, and a probability of failure, notated as 1 minus P. For example, if a machine making parts created defects in 5% of the parts, then you have 2 outcomes for each part made. Either the part will be defective or it will not be defective. In business terms, pulling a defective part would not be deemed a success. However, in statistical terms, we are not talking about the quality nature of the outcome. We are talking about whether an outcome will successfully match the definition we have created. In this case, whether the outcome will be defective. The binomial distribution of the data described on a histogram might appear as follows. For this example, P, the outcome that the part will be defective, equals to 0.05, and 1 minus P, the outcome that the part will not be defective, is 0.95. If you select one random part, the chance of getting a defective part is 0.05. First, we said that the probability of success was noted as P. Then, we said that the probability of pulling a defect part is P, or 0.05. When you are dealing with binomial datasets, you can use the binomial distribution probability function to determine the probability of the number of successes you'll have within a given number of trials, given the sample data you have. The answers generated by the binomial distribution probability function correlate to the histogram generated by Minitab we just saw, given the same information. To understand what we mean by this, let's consider the example of the coin toss again. For this example, imagine a coin is tossed 10 times and we consider heads to be success. The chance of success, heads, for each flip is 0.5. Given that information, Minitab creates the following histogram. This graph shows that if we toss the coin 10 times, the chance of getting 1 success in all those 10 tosses is very small, as is the chance of getting 9 successes. The chance of getting 5 successes out of 10 is much higher, but not actually 50%. To apply this concept to a real-world situation, let's look again at our machine process, which produces defective parts at a rate of 0.05. Again, the histogram illustrates the data that might occur if we took 20 random samples from the process. The probability that we'll have 0 successes or defective parts in our sample of 20 is a bit over 0.35. The probability that we will have 1 defective part is a bit higher, but the chance that we'll have 5 defective parts in 20 is very, very small. The probability of more than 5 defective parts in our batch of 20 is almost non-existent. What does this tell a real-world Six Sigma team? Imagine a quality control team took 20 random samples from this process every day. For 2 weeks straight, the quality team records no defects within those samples. If the Six Sigma team believes the process generates 0.05 defective parts, then a lack of defective parts in the samples shows that something has changed to improve the performance of the process. The measurement system is defective or the samples are not actually random. If you increase the number of trials to 100, the binomial distribution remains. Here, you can see that the greatest likelihood for this process is that within 100 samples, 4 or 5 will be defective. It is unlikely, given the defect rate of 0.05 or 0.05, that a random sample of 100 would ever have more than 11 or 12 defective parts. In this video, we're going to study the binomial formula. What we have done graphically, you can also do mathematically using the binomial distribution probability function. The equation is as on your screen. Pause the video and take a look at it, a good look at it. For this formula, x is equal to the number of successes desired, n is equal to the number of trials, p is equal to the probability of success in each trial, q is equal to 1 minus p, and the exclamation point indicates a factorial. Using the binomial distribution probability function, we can calculate the probability that 20 trials will yield 4 defective parts in a process that delivers 0.05 defective parts, and here you have the result. What are some reasons this type of calculation might matter in the business world or for Six Sigma teams? Consider a company that sells chocolates. If 20 chocolates come in each box, what is the chance that a customer might receive defective products in his or her box? What is the chance that a customer might receive more than one defective chocolate? Teams can calculate these probabilities after sampling data to determine how often the process generates defective products. What if a Lean Six Sigma team randomly samples the chocolate process and determines that the process operates at a 4 sigma level? Remember that at 4 sigma, a process will generate 6,210 defects per million opportunities. Let's assume that means 6,210 defective chocolates per million created, or a chance of a chocolate being defective equal to 0.00621. In a box of 20 chocolates with p equals 0.00621, Minitab generates this binomial histogram, which you can see on your screen. From the previous histogram, you can see that the likelihood of a box having no defective chocolates is approximately 88%. The likelihood of a box having 1 defective chocolate is approximately 10%. And the likelihood of a box having 2 or more defective chocolates is almost non-existent. So what does this mean for the business? It depends on the goals of the business or the Lean Six Sigma project. If the Lean Six Sigma team was tasked with improving customer satisfaction or decreasing the rate of return of chocolate boxes, then a 10% probability of a defective chocolate in a box might be something the team wants to address. However, if customer satisfaction is strong and return costs are low, then the potential complaints or returns associated with a small number of boxes might be acceptable to the business, particularly if a Lean Six Sigma team discovers that reducing the error rate would cost well over the amount that it costs to handle the errors. By applying the binomial distribution in this manner to pass, fail, yes, no, or defect, no defect, Lean Six Sigma teams can calculate data that is useful in a variety of real-world situations. Teams can speak in terms of the probability that different processes or outcomes will cost varying amounts of money, or save varying amounts of money, both of which are metrics company leadership will be interested in hearing. In this video, we're going to study the Poisson distribution. The Poisson distribution is often used when dealing with data that is distributed randomly within time, distance, or other unit of measurement. For example, the distribution might be relevant when dealing with calls per hour in a call center, traffic accidents per week, or specific block or street, or even number of defects in a batch. In fact, the word per in a metric is a good indication that the Poisson distribution might be useful. In the coming slide, you'll see a graph, and you'll notice the Poisson distribution, and it can look a little like the normal curve, but it is not symmetrical. This curve, based off a mean of 4, tails slightly to the right. This graph of a Poisson distribution with a mean of 42 looks even more like the normal curve. If you look very close, however, and count the beans to the left and the right of the mean, you can see that the curve tails very slightly to the right. This is a good example of why statistical analysis is needed in addition to graphical analysis when working with data. Data can approximate the normal curve on a graph without being normal. One interesting thing to note about the Poisson distribution is that it relies closely to the exponential distribution. Remember, the Poisson distribution is discrete, not continuous. The distribution is an analysis of how many of one thing occurs per another. For example, consider the number of errors in a data entry employees work each hour. Pause the video and just quickly check the table I'm presenting you right now. That's the raw data for our next chart. And here is the histogram of the previous data. The data isn't continuous. Instead, it is categorical. How many errors does the employee make in hour 1, hour 2, hour 3, and so forth? However, if the process is following a Poisson distribution, then the time between each event in the process, when looked at, continuously yields an exponential distribution. Understanding this relationship can help Lean Six Sigma teams convert Poisson distributions to exponential distributions when necessary for statistical analysis. The use of this conversion within Lean Six Sigma environment is not likely to be common for most teams, but could be useful in special applications. The Poisson distribution might be applicable when the following statements can be used to describe your data. Data describes events that occur at a random interval measurement. The word per is usually involved. The sample size, or the number of intervals, is at least 16. If you're measuring, for example, per hour, you have at least 16 hours worth of data. If you're measuring per foot, you must have at least 16 feet of data. You know that the population size is 10 times the size of the sample or bigger. If you're measuring worker productivity, for example, you can't take the first 16 hours the worker is on the job. Event occurrences are independent of each other. In our data entry example, if we are counting each unnecessary keystroke as an error, we might count the backspace. However, the backspace is dependent on the person making another error. If the person types B when he or she meant N, that's one error. If we count the backspace as error 2, then the errors are not independent. The probability of occurrences is less than 0.1. Consider the data entry example I just introduced you to. When using a 10-key number pad, the average rate of entry for employees in the United States is approximately 8,000 per hour. If an employee is making 8 to 12 errors an hour, the probability of an error for each keystroke is well below 0.1. The rate of occurrence per interval is constant. The average number of phone calls per hour is 50, and the average number of errors per hour is 6. In this video, we're going to study the Poisson distribution equation. If data fits the Poisson distribution, you can use an equation to determine the probability of certain events. The Poisson equation is as on the screen. Within the Poisson equation, E equals the Poisson constant, which is 2.71828. Mu, the Greek symbol, is the mean or average of the process. X is the specific case or data point. And remember that the exclamation point indicates a factorial. For example, if a Lean Six Sigma team was working to improve processes in a call center, they might have gathered data that indicates the average number of people on hold for a customer service representative at any given time is 10. Given that information and a Poisson distribution when considering number of holds per increments of time, the team can use the Poisson equation to calculate probabilities related to various call scenarios. So, using the Poisson equation, let's calculate what is the probability that there are 15 callers on hold at a given time. So here's the formula applied, and here's the result. Let's think about what we just saw. The probability of having exactly 15 callers on hold at any given time in the call center is 0.035, or approximately 3.4%. That number in itself isn't extremely helpful to a business or a Lean Six Sigma team, unless there is a specific protocol or process problem that occurs only when call holds hit exactly 15. It's not an extremely likely scenario. However, what if a Lean Six Sigma team has noted that when the number of callers on hold hits 15 or above, a regularly staffed call center team is unlikely to catch up, resulting in continued high hold times and volumes? Knowing this, the team might inform the process owner that when hold number hits 15, it's time to move some resources from other areas to answering calls. In this video, we're going to apply Poisson's equation. Before moving on, please, if you haven't watched our previous video, you have to, because the coming calculations are based on the sample scenario we started back in our previous video. So, how does a process owner or a Lean Six Sigma team plan appropriately? Do other resources in a call center need to constantly be on hand? Is the probability of this situation occurring high or low? Remember, we're talking about that moment when, at any given time, the number of callers on hold hit 15. And to answer the questions I just made, you can use the Poisson equation to find the probability of there being 1, 2, 3, 4, up to 13 and 14 callers on hold at any given time. Because the probability of all possible outcomes totals to 1, you would subtract the sum of all those probabilities from 1 to determine the probability of the number of holds being 15 or more. Mathematically, the concept is written as you can see on your screen. To manually calculate the probabilities, you'd have to use the Poisson equation for each P listed on your screen. You can also use statistical analysis software such as Minitab to make the calculations for you. We'll cover how to handle such analysis in Minitab in later modules. For now, though, consider the chart on the screen which shows the probability of each X. Summing the probabilities for each X provides a total probability that X will be less than 15 of 0.91. Alternatively, you can use statistical software to determine the cumulative probability, the area under the curve to the left of a certain point. The cumulative probabilities of X being less than or equal to 14 is 0.91. Therefore, the probability of X being 15 or greater is 1 minus 0.91, or just 0.083459. The probability that there are 15 or more callers on hold at any given time is about 0.083, or just over 8%. Given this probability, call center leadership can make a more educated decision about whether they want to pay for more staff or take a risk at hitting the higher call volume and having to play catch up for the rest of the shift. Teams can use the Poisson distribution calculations in this manner to understand the probabilities of different events occurring. They can also tie financial data to such events to make even better data-driven decisions. In this video, I am going to teach you about geometric distribution and negative binomial distribution. The geometric distribution is used when there are two outcomes for a trial. Trials are independent, and there is a waiting time before the first occurrence. As with the binomial distribution, the outcome of each trial must be independent. A real-world use of the geometric distribution might include the number of inspections that occur before finding a defective part, or the number of resumes or applications a recruiter reviews before finding the first candidate that meets minimal job requirements. An example of the geometric distribution can be seen on your screen. Pause the video and analyze it. The negative binomial distribution is also used with attribute data, fail or pass, and other situations, where there are only two outcomes for each trial. Again, the outcomes must be independent of each other. The probability of an occurrence must be the same across each trial, just as with the binomial distribution. Throughout this module, we've touched on some ways that probability distributions let Lean Six Sigma teams apply raw data about processes to real-world concerns and situations. As previously stated, many of the statistical analysis you'll perform on data will be related to the normal curve. But understanding a few equations related to distributions such as binomial or Poisson helps you expand your ability to create real-world assumptions about data. When you can determine the probability for certain events or data points, you can make educated decisions about a process. What is the probability that a cost-heavy event will occur? Is the cost associated with an event enough to create a reason for working to reduce the likelihood of that event? If the probability of a low-cost effect is high, are the total expenses associated with that effect likely likely to be higher than the total expenses associated with a high-cost effect that has an extremely low probability? These are just some of the questions that teams can use statistics and probability distributions to answer. That's it for now. I'll see you in our next module.